So thank you very much for the invitation. It's a pleasure to be here, and thank you for the kind introduction. I'm glad that you left some time for the talk itself. So without further ado, let me go on and start here. So the pictures I'm showing here are some pictures from University of Illinois. We have a new electrical engineering building that we're very proud of. It's a zero energy building designed to use solar energy and conserve energy. Solar here is no big deal. Of course, you have the sun all the time in Illinois. Having something which is solar powered and zero energy, it's more of a challenge, but we made it. So what I'd like to tell you about today is an overview of work over a number of years. And what I'd like to tell you is that sparse models are useful, and I think many of you may be already convinced of that. What I'd like to emphasize is that learning them from data is even better. So that's one aspect. The other is that there are several competing learning models, and I'd like to tell you that, or convince you that the transform learning scheme that we propose is particularly effective and competitive with other methods, and it leads to state-of-the-art results in various applications. We have studied maybe just a bit. We scratched the surface, image and video, but people here already talked to me about using it for a host of other applications, such as audio, spectroscopy, whatnot. So really your imagination is the limit of where this can be used, because these are models for data. If you have a good model for data, you can do everything. If you have an excellent model for data, you don't need the data, right? So we don't go as far as that, but good models are obviously useful. Okay, so I'll start with a view of sparse models for data, and I realize that many of you already are familiar with some aspects of this, so I won't dwell too long on this, but I want to define the terminology here and get everyone on the same page. And then I'll describe the method which we call transform learning, which is this. So that's in distinction to learning synthesis dictionaries, which is what, if you look into learning, dictionary learning in literature, you'll find mostly these. And our innovation, so to speak, is in transform learning. Then we'll see a few variations on the basic scheme, which is learning a union of transforms, in some sense a bag of transforms, and then an online scheme, which is useful for big data or for streaming data, such as video. And finally, for those of you who are kind of in hardcore signal processing, you may remember your DSP courses where you learned about filter banks. We'll see that there is a point of view of some of this work from a filter bank perspective. That perspective connects it potentially to things such as convolutional networks in deep learning. And I had a question already before the talk about this, so we'll see that there are some potential connections which we haven't fully explored those connections, but we have results using a structure which is similar to a single layer convolutional network, and we see the advantages of doing that. Okay, so why sparse modeling? Why would you want to model something as being sparse? Well, it's because sparsity is all around us. So here's a famous image, the image of Barbara. You know that the image of Lena has been banned, so to speak. But actually, she made an appearance in one of the, I think in ICASP, and she was actually quite pleased to have her picture used. So maybe it should be brought back in. But in any event, this is a wavelet decomposition of the Barbara image. We see here the coarse detail, and then these are the detail images. And we see they're mostly black, meaning they're mostly zero. So they're sparse. So if you represent an image in the correct basis or in the correct transform, you'll get something that is largely sparse, largely zero. So sparsity is around us. It's not evident when we look at the image. This image is not zero or doesn't have many zeros, but properly transformed, it does. So another way to express this is to say that the data lives in a union of low-dimensional subspaces. This is an example of a data set that lives in a union of one-dimensional subspaces, almost. It kind of deviates, the green dots, the data deviates from this model, and then that's what always happens. A model is a model. Reality doesn't obey exact models, but often the models are a good approximation. Okay, what are the applications? So one very famous application is compression, getting a compact representation for data. So classically, We know that JPEG works by taking 8 by 8 patches of images, computing a DCT, discrete cosine transform, which is like an FFT. And then what you find is that many coefficients, after you take the transform, are 0, as we've seen in the wavelet transform here. So then you don't need to spend bits on them. So that's really the idea behind compression using sparsity. But other applications are inverse problems. So in general, inverse problem is something where you don't get direct measurements. So if you take a picture, you get pixels which correspond immediately to the image. That's a direct measurement. But often the measurements are indirect, such as in tomography, where you shine X-rays through an object, so you don't get the pixels of the object, you get line integral, a collection of sums through those pixels. And you have from that to unravel the object. So there are many inverse problems. Some of them are simple, such as denoising an image, but other can be recovery from degraded data and compressed sensing. And I'll spend a bit more time talking about this. Another area is classification. If you want to classify objects, having good model for them again is very useful. Okay, so I'll talk about mainly two models. One is the synthesis dictionary model, and the other is the transform model, which is the one I'll describe in great detail in this talk. So I'll set this up as the background because this is what you'll find mostly in the literature, and I'd like to show that we have advantages by studying a somewhat different model. Okay, so what's the idea here? So we have this model where we model data y, data vector y, as a matrix D multiplied by some vector, and the vector is sparse. Sparse meaning has only a small number of non-zeros. Okay, so mathematically you write it like this. So this has become a notation which is read the zero norm of A is less equal to S, but this is not really a norm, it just counts how many non-zeros we have. In this case, the zero norm of A will be 3, the number of non-zeros. Okay, so A is a sparse coefficient vector. D is called a dictionary, okay? Because we are expressing, one way to think about it, we're expressing the word Y as a combination of words or letters from the dictionary. Or maybe Y is a sentence, we're expressing Y as a combination of words from the dictionary. And then the columns of D are called atoms. And this is actually a different metaphor. What's the atom metaphor? Well, Y is a molecule. We're combining elements from the periodic table. So each column here is an element in the periodic table. You take a small number of atoms and form your particular material. Okay, so chemicals are actually sparse combinations from the periodic table. And then the vector Y, our molecules, belong to a union of subspaces spanned by columns here, by a subset of columns. Okay, so that's the kind of mathematical structure we have here. So this is known as the synthesis model because we're synthesizing this object, this molecule, from the atoms. And A tells us what are the components, which atoms we take, and how many of each to form this. Okay, so now we have a problem which we call sparse coding, and I emphasize this here because this will be a term I'll keep using, so make sure you follow what sparse coding is. So here's the problem. You're given a dictionary D, and when I say it's overcomplete, it means it has more columns than rows. So it's kind of a fat matrix. We're giving such a dictionary and a vector Y, and you would like to express it in this form where A is sparse. Okay, so mathematically it means the following. We want to solve the following problem. Find the sparsest vector such that Y can be expressed as a sparse combination of the columns of D. Okay, so this is known, solving this problem is the sparse coding problem. So again, in the chemist metaphor, you have a molecule, you'd like to find out which atoms make the molecule and how many of each. Okay, this is the sparse coding problem. Turns out that this problem is NP hard. Okay, so what does it mean? It means that in practice, you cannot solve big problems because it becomes intractable computationally. Well, the good thing is one can look for approximations. That's what we usually do when we have hard problems. And here is a list of some approximations that have been proposed in the literature. So one is convex relaxation. You replace this zero norm by the one norm. One norm, which is the sum of absolute values. Turns out that if you do that, the problem becomes sort of easy. It becomes a convex problem, and you can solve it, for example, using a linear programming code. Okay, so there is an iterative algorithm. There is quite a bit of computation that goes into it, but it's no longer NP hard. It scales in a much more favorable way and becomes tractable. So that's one class of solutions. Another class of solutions are greedy algorithms. Okay, there is actually a paper entitled "Greed is Good." Okay, and why is greed good? How does greed work? Well, you look for elements one at a time. So first you try to represent y by a single atom. You find the best atom that gives you the best approximation to y. Once you've done that, you subtract that from y. Then you look for the next atom to represent the residual. And you keep doing that. So that's a greedy method because it picks one element at a time. It can be shown to actually fail in certain cases, but it's a reasonable approximation here. Okay, so there are methods to solve this sparse coding problem, but they're somewhat expensive. Okay, well, suppose we know how to solve sparse coding. How can it be useful? Why would we bother to solve this problem? So here's an example of how we could benefit. So here the data set, the green dots, are almost on these subspaces spanned by the columns of the dictionary. If we know the dictionary, we could try to eliminate the noise by projecting them onto these red lines. Okay, so we would, doing that, we'll get this. And we've removed the noise component, which was perpendicular to these red lines, to these subspaces. Okay, so this is a way to achieve denoising, and you do this just by doing sparse coding. Okay, so solving sparse coding can be useful, and it's often done. Okay, so we know about synthesis dictionaries, about sparse coding data into a synthesis dictionary. What are good dictionaries? Where do you get the dictionary? Who gives you the dictionary? So, and if you are given a few dictionaries, which one will you pick? So the best dictionary is the one that gives you the more sparse representation. Okay, because if you just had your dictionary was the identity matrix, you can represent any signal as a combination of the columns of identity matrix, but then it's not going to be sparse in general. So if someone gives you a good dictionary, it means you can achieve a sparse representation. And the sparser, the better. Okay, so that's the choice of a dictionary. Where do those come from? Well, for many, many years, what we did, we looked into theory, and those theory which told you for certain signals, Fourier bases are good. For other signals, wavelets are good. Yet for other signals, curvelets, contralets, whatnot, there were mathematical arguments to tell you what bases or transforms you should use to get sparsity. Turns out that all this theory works for one-dimensional signals. Once you go to 2 dimensions like images, that theory breaks down. There's actually no theory which tells you how to pick a good basis for that. Okay, and there are some kind of ad hoc solutions by looking into essentially Kronecker products of these one-dimensional bases, but those are no longer optimal from a theoretical point of view. The good thing about them, they have fast implementations. You have n log n type algorithms to compute them, but for higher dimensions, you cannot get good dictionaries using these. Well, we're getting to the idea of this talk, which is learn. Okay, you have data. Learn from the data what is a good dictionary, which will give you sparse representation. Okay, how do you do learning? So I guess in school we learned about the Karun-Loew transform or principal component analysis, essentially a single value decomposition of the data or an eigenvalue decomposition of the covariance. What does that give you? Well, let's see an example. So here's our example data. The green dots. We ran PCA, principal component analysis, and what it gave us is this. One vector really captures quite a bit of the data. The other vector, on the other hand, is kind of useless. It's trying to capture these other 2 linear clusters, but it cannot do it, and it's constrained to be perpendicular to the first, and it's really useless. So PCA is not going to do the trick. We need a different method for learning. Okay, what do we do? Well, let's just pose the problem and see if we can solve it. So this is the problem. We have training data, vectors y1 through ym. We want to represent all of them as sparse combinations from the elements of a common dictionary. Dictionary is fixed, and we're going to pick different sparse combinations, different sparse vectors. But now we want to learn a common dictionary that will allow us to do this for this data. So the way to set this up, we take all the training data, put them as columns side by side into a big matrix. That's a matrix Y. And then we're saying we're looking for dictionary D and matrix A, which has these sparse columns, so that we get this good approximation with the columns being sparse, having fewer than S components per column. Okay, so this is the dictionary learning problem. So we set up the problem. The problem is easy to set up. To solve it is more difficult. One reason for the difficulty is this. You're given Y. What you want is to factorize it into a product of 2 matrices, D and A. A is sparse. Well, finding such a factorization is not obvious at all how you'd go about it. Okay, so not a trivial problem. In fact, it's a hard problem because to solve it, essentially what you do, you can think of, you guess a dictionary. Whoops. Let's see. I want to go back here. You guess a dictionary, and then you find the sparse solutions. Result is good, good, you stop. It's not good, you change the dictionary a bit, tweak it, and resolve the sparse coding problem. So you have to solve the sparse coding problem many times. What you're seeing the sparse coding problem is NP hard, and you have approximations, which are expensive, so the whole thing can be expensive. In fact, the problem is non-convex, so you can get stuck in some local minima. So there are various algorithms, various heuristics, so to speak, and they sort of work, but they can get stuck in local minima depending on where you initialize. Okay. So in summary, the good thing about the synthesis dictionaries is that give you sparse models and you can learn, so that's good. There are many successful applications. You can, if you look in the literature on dictionary learning, you'll find many interesting applications: denoising, inpainting, image super resolution, compressed sensing, classification, all whatnot. So it's a very useful strategy. The trouble is that is this cost, because you're approximating an NP hard problem, and the fact you can get stuck in local minima. Okay, is there anything else you can do? Can you do better? So I wouldn't be here if we didn't think so. And the idea is, let's go back to what we learned in school, which is transforms, using transforms to sparsify data. So here's the idea. This time, you have a data vector, and we'll apply to the data, we'll apply a transform, which will produce a sparse vector plus some residual. Okay? So we call W a sparsifying transform. Z is called the sparse code. And what we want is W times X to be approximately sparse. So this has to be small. Okay, now this is not new. This is how JPEG works. You take, again, blocks of patches of the image. These are the vectors X. You apply DCT to them, and you get something mostly sparse plus some residual. You say, I'll forget about the residual, and you just assign bits to these guys. I mean, that's roughly what JPEG does. So we have been doing it for many years, but somehow, once we got to learning, this scheme got forgotten. And instead, there was a switch to this dictionary learning, and people learned synthesis dictionary. What we said, let's see if we can learn instead, learn transforms. Because if you learn transforms, the sparse coding, we'll see, is easy. Let's see how that works. Okay, so what is sparse coding here? We have a vector X. We apply the transform to it, and we hope that the result is sparse. So we want to fit it by a vector Z, which is sparse. We want to solve this problem. So this is the sparse coding problem for transforms, not for dictionaries, but for transforms. Okay? Looks, again, kind of difficult. You know, we have the sparsity constraint. How do you do this? Well, it turns out, actually, this is a very, very easy problem. How do we do this? So this is a sparse vector, and you ask the following. What is the best sparse vector to approximate this so that the residual is small? This is not sparse, but you want to find a sparse approximation. The idea is this. If you're limited to S non-zeros in this vector Z, what do you need to do? Take the S biggest elements in WX and kill those. And after that, you're left with small elements. Okay, so what we want to do is pick for Z the S largest elements. That's all we need to do. So that's a simple strategy thing. You compute WX, sort it, take the S largest, and you're done. That gives you the vector Z. Okay, so this is what actually JPEG is doing. So JPEG couldn't work, you know, in the olden days. You didn't have a supercomputer in your pocket. So JPEG was implemented on chips, and the chips have to be efficient. You know, there were discrete gates in that chip. You could only do it if you had a very, very simple algorithm. And transform coding is simple. That's why it worked, and that's why it was so popular. Now we got spoiled by the computation we have at very low cost, and we forget about the simple solutions, and we do dictionary learning, synthesis dictionary learning, which is expensive, but you can still get lots of good papers published because, you know, you can compute. Yes?
So the difference between this and a dictionary problem is that it's more
No, the difference is, I'll in a moment show that contrast the models. The difference is, here we apply the transform to the data. W times X should be sparse. In the dictionary model, we say the data is equal to something, to a dictionary, times something sparse. We have a product of unknowns. Here we don't have a product of unknowns. Here we have W, which is unknown, times a known. This is data, and here we have an unknown. So we've eliminated the product of unknowns, and that essentially simplifies the problem. And we'll see that in a moment when I contrast them.
The
Yes?
optimization problem looks similar between the two tests?
So kind of superficially it looks similar, but for this, as I showed you, you get the optimum solution by a trivial step where you take this, find the S largest values, and that gives you the answer what you should put into Z. For the dictionary sparse coding, it's an NP-hard problem. So obviously the problems are different. Kind of superficially you don't see that. You have to think about it. Proving that it's NP-hard, you know, that took a paper. Natarajan showed this in 1995. But it's easy to see that this is easy. That the other one is hard is not obvious, but if you look at it, you don't know how to solve it either. So, yeah. Okay, so I just want to show a slightly different flavor of this. Instead of constraining sparsity, you can add a penalty which is related to sparsity. So here we have again fitting Wx, which is not sparse by a sparse vector, and we do this by penalizing the number of non-zero components. So now the optimization problem is formulated like this, and turns out that this one also has a very easy solution. You take this element by element. If the element is bigger than square root of this constant nu, you keep it. If it's smaller, you set it to 0 and you're done. So again, a simple thresholding algorithm called the Howard thresholding gets you the result. Okay, so here's a summary of the models. Let's look first at the top. This is the synthesis model. So finding X with a given D is NP-hard. So this is what we're trying to do. Given Y, we're trying to find X such that we can approximate Y where X is sparse. Okay, that's the problem here. Turns out that this is an NP-hard problem. At the bottom, there is the transform model. Here we have data Y. We apply W, the transform, known transform, to it in this case, and we're looking for something sparse here and a small residual. And this is easily solvable by thresholding. So that's the difference. Whereas here, we're trying to express Y as a combination, sparse combination of columns. Here, we're trying to sparsify a vector, which we compute directly. There's yet another model, which is called the analysis model, and this is called the noisiest thing analysis model, which I won't drag you through. Also NP-hard, it's a different flavor of this. So the same people, Miki Elad is one of the leaders in playing with synthesis dictionaries, and he has also studied this, and a few other people have done that. And these two are comparable, and in difficulty they're also comparable. Doing this, suddenly the difficulty is diminished significantly. So from now on, I'll focus on this transform scheme. Okay, any questions at this point? Yeah.
So number 3 is easy if you know W.
Exactly, yes.
Right? Number 1 is difficult even when you know D.
Exactly, yes.
Right? But that's only the case if D is not square, I think, right?
Even if D is square, if it's not orthonormal, it's hard.
W is constrained to be orthonormal.
No, we're not constraining W to be orthonormal. W can be arbitrary, we'll see that. Yeah. In fact, we'll see that there is an advantage to W not being orthonormal. It gives you more degrees of freedom. You can find better sparsifying transforms than what you can if you're constraining to be orthonormal. So we relax that. Okay, so how would you apply this entire business to images? So where do you take those training elements? So here's an image, and what we do, we take patches from the image, and in fact overlapping patches. So we slide this frame over the entire image. We extract all these patches. Each patch is, say, an 8x8 matrix. We turn that into a vector of length 64, and now we have our training data. So from one image, we can extract as many patches as there are pixels because we slide the patches into all positions. So if you have an image which is, say, 1K by 1K, we can extract from it 1,000,000 patches. Each of them has 64 pixels. Okay, so we have lots of training data just from one image. Okay, we don't need to train on many images. And just notationally, what we do, this R sub j extracts the jth patch. So yj is the jth patch extracted from the image y. Then we can take all these patches, turn them into vectors, put them side by side, and we have the training matrix Y. Okay, so now comes the interesting part where we have to learn the W. You don't know the W, and you like to find a good W. Well, what does it mean good? What we want is to WY to be well approximated by X, which is sparse columns. Okay, so that's what we want. We don't know X, we don't know W this time. So we have to solve for both. So we just pose a minimization problem, and we want to minimize this deviation, so we want the model to be good. Find a good W, find a sparse X. Okay, so this is the problem. Now notice that here we don't have products of unknowns. W is an unknown, but it multiplies the known data, and X is not multiplying anything. So we don't have products of unknowns. In this sense, this is a very nice quantity. F here stands for the Frobenius norm, which is just the sum of squares of all the elements. Okay, so this is the problem, but yes? S. Okay, very good question. How do you know what sparsity? So in principle, you can solve this for many values of S. If you don't know a priori, you play with it and see for what S you get a good fit. And in fact, that's what my students did for a while, and we found that for many, many images, S, which is on the order of 10% of the length of the vector, works. So, yeah. Okay, so then turns out that this is a good formulation, but not good enough because it has a trivial solution. The solution is W equals 0, X equals 0. Then this quantity is 0, and that's the smallest it can be because it's not negative. So not very interesting. Well, to make it more interesting, you have to constrain W from being stupid. And the way to do it, or one way to do it, is to add this term. Okay, so that looks complicated. It's not that complicated because what we have here is this. We have the determinant of W. That could be negative or positive, so we take a magnitude to make it positive. Then we take a logarithm of that. Okay, what does this term do? What it does, if W is 0, determinant is 0, and then the log will be negative infinity, and then negative log will be infinity. So this is something that prevents W from being 0. If W is 0, this blows up to infinity, but we're trying to minimize, so W0 equals 0 is no longer a solution. In fact, this thing does another good thing. It prevents the rows of W from being the same. If you have two rows of W which are the same, you have rank deficiency, you have the determinant equals 0 again, and that gets rejected. So what this does, it prevents trivial W. Furthermore, by adding this term, we can show that we get a complete control over the condition number. So we can set lambda to get any condition number we want for this matrix W. So we can control the condition. A well-conditioned matrix is good if you want to invert it, for example. It doesn't blow up your error. Okay? Okay, so that's the formulation, and this looks like a complicated optimization problem. In fact, it is. It's a hard optimization problem, but the way we solve it is we alternate. That's a common way to address such problems. So we say the following. Suppose someone already gave you X. You're lucky someone gave you W. So you know the transform. You just need to solve this. This is the sparse coding problem. We know how to do this. This is just thresholding. Cheap. Easy. Okay, so this is easy. Okay, now suppose you found X. Now you want to solve for W. You have to solve this problem with X fixed for W. This actually looks pretty ugly here with a negative log determinant and so on. Turns out, magically, it has a closed form solution. So we can compute the solution, which gives you the exact global optimum for this in terms of a singular value decomposition. We take the data Y, form some matrix, do a Koleski decomposition, plug it into, compute some other matrix, do a single value decomposition, take the results, plug it here, and we have a solution. So a simple, maybe 3-step procedure. In MATLAB, you hit a key, it immediately happens. You cannot even blink before it happens. Okay, very, very easy computation on a small matrix, and you get your result. So solving this is trivial, solving this is trivial, and now what we do, we alternate between the two. Okay, so our scheme is this. You start with some initialization, so maybe we start with initial guess for W. So DCT is used in JPEG, so maybe it's not a bad transform. We start with that as initialization, and then we iterate, update W, update X, iterate a few times, and we have the result. Okay, how does it work? Well, you can't get a PhD without proving a theorem. My students prove various theorems about this and show various convergence properties and so on, but I won't drag you through those. Let's look at how it works in practice. Okay, so here's what we did. We took the image of Barbara, we extracted the patches from it, and those are our training set. We'll learn all the patches. We're looking for a transform which will sparsify the patches. So here's the objective function, which I showed you before. Different initial points, different initial values, and from different initializations, we convert. So it doesn't matter really how we initialize. In each case, you convert to the same cost. And the condition number converges. We get a good condition number between 1 and 2 here. And let's see what we learned. So we'd like to show you the W that we learned. Now, W is, in this case, a 64 by 64 matrix. So if I threw a matrix of numbers, that wouldn't be very interesting. So one way to display this is to take every row of this matrix, it's a length 64 row, convert it back into a square of 8 by 8, and then display it in grayscale. That's what we did. So this is a display in grayscale of the rows of the DCT, discrete cosine transform. Each such patch corresponds to one row of the DCT. And you see the known structure, kind of sinusoidal structure along both axes. Kind of low frequencies here, higher frequencies here, and so on. This is what you learned, the W you learned on Barbara, initializing with the DCT. So it's kind of somewhat similar to the DCT, but you see it has a fire alarm. No.
Maybe an interference between the two mics.
Doesn't repeat. Okay. All right, as long as there's no need to run for shelter, I think we're okay. Okay, so this is what we learned. You see that it kind of has a similar property of low frequencies and high frequencies, but you see here diagonal components where you don't see the diagonals here, and there are some other things that we learned from the data. If you look at Barbara's pants, she has these diagonal structures running here, the tablecloth likewise, so kind of makes sense that we'll learn some things which capture diagonals as well. Okay, well, let's take a simpler image for which we can have even better intuition. So here's a variation of Mondrian here, and it's an image which is piecewise constant. Okay, so a very simple image. How do you sparsify this? So if you know nothing and you start in the prehistory, you know how to sparsify such images. All you need to do is to take pairwise differences of pixels, because if your pixels are in a constant region, taking a pairwise difference creates 0. So taking pairwise differences on a piecewise constant image gives you a sparse quantity. So this is the finite difference operator, which can be represented the same way I described to you before, and you apply it to this image and you get this sparse result. Basically only the edges remain. Okay, so that's not surprising. And so it's a very good sparsifying operator. It gives you something sparse, but its condition number is like 113. It's not very well conditioned, in fact, poorly conditioned. Yes?
One quick question. On the previous result
Yes.
with Lena,
Barbara.
Barbara,
Yes.
did you get the same learned W regardless of the initialization?
Very good question. No, we get different W's, but they all result in the same cost function, and they all sparsify equally well. Yes. So W is not unique. And one way to understand this is you can permute the rows of W and permute the rows of X, and the result doesn't change. So for example, all permutations give you the same result. But actually the set of alternatives is even richer than just permutations. We have a way to describe the variety of things which are equivalent, and they all perform the same, but no one is better than the other. So we just end up picking one of them depending on how we initialize. Yeah, good question. Okay, so this is a sparsifying operator not obtained by learning, but obtained by learning in school, basically, right? So this is an analytically motivated thing. What can we do if we learn it? So here's a learned transform, 2 different learned transforms, which sparsify essentially just as well, have some 10 to the -5 residuals or something, but they have a much better condition number. So by learning from the data, we can obtain better transforms than you can by just using analytical reasoning. Okay, so that's just a toy illustration here, but hopefully somewhat convincing. Okay, so beyond that, there are computational advantages. So if we consider the synthesis or the analysis algorithms. One famous algorithm is KSVD, due to Brookstein, Aharon, and Elad. Very popular algorithm for learning synthesis dictionaries. Its cost is like this. So if you have the image size in pixels times the size of a patch. So a patch is, for example, 8 by 8, so 64. The computational cost scales like this. Image size times the cube of the number of pixels in a patch. For transform learning, it scales better. This cube goes down to 2. So we're bettering the order in terms of scaling. That can be significant. In 2D, with P by P patches, 8 by 8, the computations improve by a factor of like P squared, 64 times. In 3D, if you have three-dimensional patches, each of them, say, 10 by 10 by 10, you could get an improvement by a factor of 1,000. So nothing to sneer at. So we think that's a useful thing. Okay, how does it work? How well does it actually work in some applications? So a very popular application is denoising. If you have a good model for the data, you should be able to differentiate noise and signal and reject the noise. So I won't show you the exact algorithm, but we use in one example, so we start with a noisy image, and then in one example we use the synthesis dictionary learning. We learn a dictionary and we denoise. In this example, we learn a transform, very well-conditioned transform, and we denoise. So the denoising performs not all that difference. We gain the fraction of a decibel, so no big deal. Nothing to write home about here, but in this case we run quite a bit faster, 17 times faster than this, and obtain comparable signal-to-noise ratio. Okay, so we're computational advantages here. Okay, now I want to show you another application, maybe somewhat of a killer app for this, but there may be other applications, which is compressed sensing. Okay, so what is compressed sensing? How many people are familiar with compressed sensing here? Just as a, yeah, so some have heard it. So what is compressed sensing? At a high level is the following idea. You have data Y, which is modeled as some matrix A times unknown X. So essentially you have a system of linear equations which describe your data. The problem is you have fewer equations than unknowns. Can you solve the problem? Can you get a good solution? So normally what we learn at school is no, you can't. You have to have more equations than unknowns, or at least equal number. But if you know that what you're looking for should be sparse, things suddenly become better. You don't need as many equations. You can get by with fewer equations. Okay, that's the idea of compressed sensing. So compressed sensing allows you to do this, use a sparsity. The solution is nonlinear. To solve linear equations, that's a linear problem, but to solve linear equations with a sparsity constraint is a nonlinear problem. You have to solve this kind of problem. And the way it's done is this. So you minimize the deviation between the data and the model, and you regularize with some transform applied to X, which makes it sparse. That's how you penalize for non-sparse things. If this is large, it's non-sparse. This is small, it's sparse. So you give preference to sparse results by minimizing. Turns out that if you solve this, you can get an exact solution for X, even though you have fewer equations and unknowns. And this is known as compressed sensing. So the metaphor is, normally we acquire data, we acquire lots of data, and then we compress it to put it on our devices. Well, if you're going to compress it anyway, why would you want to acquire first all the pixels? So why would you want, I know, a 10 megapixel camera if after that you compress it to 1 megabyte or 1 megabit? So somehow you should be acquiring at the outset just the important data. So you want to compress during the acquisition. So this idea of compressed sensing. So this has been popularized over the past 10 years. In fact, the idea of compressed sensing and algorithms and demonstrations of this we did in my lab back in 1996. We wrote papers about it, but we didn't have a catchy name. So this fell into oblivion. The best we came in terms of a name was image compression on the fly. So not quite compressed sensing. So compressed sensing is a better name, and maybe part of the reason it became so popular. But anyway, it's a popular approach and very powerful because once you do this, you can get the same information with less data. Less data means less expensive sensor, and that has value in every possible application. Okay, one particular application is magnetic resonance imaging. So I've for many years worked on medical imaging and MRI in particular. So what happens in an MR scanner? Well, you put your brain into the MR scanner, so that's your brain. When you put it into MR scanner, what it does, it computes a Fourier transform of your brain. Okay, so the MR scanner essentially acquires Fourier transform, and what it does, it takes samples of the Fourier transform. The Fourier transform is called K-space data, and you take samples of this. And that's what the scanner does. To recover the brain, what it does an inverse Fourier transform using FFTs, basically. So that's the idea. But to do that, you have to acquire all of K-space, and that takes time. So if anyone has been in an MR scanner, you sit there, or you lie there for a while, and you bang, 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 as the currents go and collect the data, and that can take half an hour. Now, if you could speed that up by a factor of 10, I guess the hospital could make 10 times more money out of the same scanner. That would be useful. But even more importantly, imaging the beating heart. You don't have much time to acquire the heart, because if you want to acquire it in one beat, not much time, so you'd like to speed things up. So imaging moving things, imaging kids who, can't sit still on the magnet, all those things. Fast acquisition is important, so you want to be able to reduce the amount of data that you acquire and still get good images. So this is where compressed sensing shines. Okay, so this is the idea: acquire a small number of samples, but use sparsity, and doing that, speed up the acquisition. So this has been proposed before. In fact, this figure is whoops. Let's see here. Yeah, this figure is taken from a paper by Lustig et al. From 2007, and they demonstrated it on MR scanner. And what they used is they solved exactly this problem, and for this matrix psi, the sparsifier, they use a wavelet transform. So that's a good choice, and it worked, but you're kind of limited to how much you can accelerate. Turned out that they could accelerate by a factor of 2, maybe 3, mostly by a factor of 2. So not bad, but can you get better? And turns out you can get better, one, using the transform learning scheme. So we'll learn a sparsifying transform from the data, and instead of using DCT or using wavelets, and we can do better. And you can also pick a better sampling pattern. You can pick a clever way to acquire, which is different work, and I will describe it here. Okay, so here's the idea. What we do, we call it transform blind compressed sensing. Blind because you don't know the transform. You're also trying to learn the transform. At the same time, you're acquiring limited data, and you're trying to recover the object. So one approach is use a database to train the sparsifying transform. So suppose you image lots of people, you have lots of brains, you learn the transform on that corpus, and now when I come in, I have my brain imaged and reconstructed using the transform that was learned on a corpus. That's not a bad idea, but it has two drawbacks. One, every brain is a little bit different. So learning on my brain specifically would be better than learning on the corpus. But you can't learn on my brain because you don't have it yet, because you haven't acquired it. And I want to acquire it using limited data. So how can that happen? That's kind of the challenge. Another reason not to use the corpus is often you're looking for abnormalities. So if you train on normals, you may not learn something that's applicable to the abnormality. Okay, so what we say, let's learn on the particular object that we're trying to reconstruct. So we want to learn the sparsifying transform to sparsify the unknown image using only the undersampled data. So this A gives you only a fraction of the components of the data. Learn on that. So we want a model which is adaptive to the underlying image, which is unknown. And then we want to use a learn transform to recover the image, which is unknown. So if you've been following, you realize we have a bit of a chicken and egg problem here. Because if you have the image, you can learn the transform. But if you don't have the image, how are you going to learn the transform? If you can't learn the transform, what transform do you use to do compressed sensing? So it's kind of a chicken and egg problem, but one way to overcome it is to throw everything into an optimization formulation. So we have here a formulation that says, here is the unknown image. We extract patches. We apply sparsifying transform. We want to get something sparse. Make this small, meaning it's sparse, so we constrain these B to be sparse. Here's the data fidelity. Your result should satisfy the equations of acquiring the data. And then here you want to prevent some trivial W. And then you want to minimize this now over the unknown transform, the unknown image, and the sparse representation. Okay, so this is the problem we have. We have some extra constraint here, which is not important. And again, we do alternating solution. So suppose that you somehow guessed an initial guess for your image in a transform, then you have to do sparse coding. We know this is cheap, easy thresholding. Next, you have to learn the transform for fixed sparse codes and fixed image. Again, we know how to do this. Has a closed form solution, easy. And then finally, we have to solve a least squares problem, essentially. Again, standard problem, easy. So we have easy steps, which we iterate, and we get results. So here's an example of how this works. Let me see, did I skip one? No. Okay. Yes. Okay. So this is a reference image. So that's what we'd like to get. And that's what we would get if we acquired all the data. What instead we do, we acquire data here. So this is the Fourier domain, and the MR scanner acquires data along these bright lines. The black is not acquired. So in this example, we have 7-fold undersampling, meaning we only acquire 1/7 of the full data. So if you just do an inverse FFT, you'll get junk because you acquired only 1/7 of the data. Okay, so here is the result using our approach, which we call transform learning MRI, TLMRI. Good recovery, visually not distinguishable. To see more detail, we take this minus that, the difference, and this is the difference. Again, not much difference between the recovered and the reference. A different method, this is the Lustig et al. Method using wavelets for the transform. This is the error in their recovery, and they only get 25 dB, so we get almost 6 decibels better in terms of signal-to-noise ratio. This is a method based on synthesis transform learning. So I've been telling you for the past, almost hour now, that we do better than synthesis, both in speed and quality. But before we started work on transform learning, we did work on dictional learning. We applied it to MRI in 2011. And this is the result, the error that we have for that. So the error is not as small as this, but it's better than this. So learning is better, but this was synthesis learning. This is with transform learning, we do even better and much faster. Okay, here's another example. This time again, comparing the reference image. We're acquiring the data now in a different pattern in K-space. This is our recovery error. So our recovery is essentially indistinguishable from the reference. This is what we get with our older algorithms, which use a synthesis dictionary. There is a difference of about 2 decibels, and the error is higher. So we get smaller error, we get faster recovery using this strategy. Okay, so far we've seen the basic scheme. So we have a transform. We learn this transform from the data. We can also learn it from partial data, which you acquire using, when you do compressed sensing and you acquire only partial data, you can still recover. So I want to quickly take you through a few more variations. How are we doing on time here? Okay. So one variation looks into the following problem. Look at this picture of Barbara, and you'll see there are various textures. And what we have been doing, we've been extracting patches from this and learning a single transform to sparsify all the patches. Why would you expect that a one transform can sparsify all these different patches which has different properties? Or this example where you have very different textures. It makes sense that if you could learn different transforms for different regions, you do better. Okay, so that's the idea of learning a union of transforms. So in this example, we would learn a different transform for each region, or in the case of Barbara, we would again learn a different transform for different regions with different textures. So this sounds like a good idea, but again, kind of a chicken and egg problem. How would you segment this before you have the transform and so on? Well, you just have to proceed boldly and form an optimization problem, which has everything in it. Has the clustering problem, has the learning problem, and here's what it is. It has many transforms now, capital K different transforms. So we have a bag of transforms that are applied to patches, but not to all the patches. One transform is only applied to the patches which belong to the Kth cluster. So if someone told you which cluster belongs to which transform, you'd apply that transform only on certain subset of the patches. And what we'll do, we'll also learn what are the correct clusters. So we'll pick clusters which are well sparsified by corresponding transforms, and conversely, we'll learn transforms for the particular clusters of patches. Okay, and then we have this regularizer here, which makes all these transforms behave nicely, and we throw this into this alternating algorithm. Each of the steps has again, it's almost trivial solution, easy solution, which we can compute fast. And we run it and it works. Okay, so what do I mean by works? So we applied it to the case of Barbara with just two transforms, two different transforms. So essentially each transform learned on a different subset of patches from Barbara, and we got two different transforms here. This is initializing by random matrices. This is initializing by the PCA. So we learned different transforms. They sparsify equally well. These two transforms are different because they correspond to different subsets of patches. We wanted to see, are they really different or are they just reshuffled? So we computed cross-correlation between every element here and every element here. This is a cross-correlation map. And the bright spots, the red spots, are where there is high correlation, but most of the spots are cold, meaning there is low correlation. So these transforms are really different. So the algorithm found two different transforms for two different subsets of Barbara. Okay, we applied it to this problem. Here's an image with different textures. Those of you who do computer vision know that texture segmentation has been worked on for eons, but it's still kind of an open problem. There is no good universal algorithm that works well for texture segmentation. It's a hard problem. Visually, we're very good at it. It's obvious to us where one texture ends and one texture starts. For algorithms, it's kind of difficult. This is the result of what you get if you apply k-means. This is a well-known clustering algorithm. Not a very good classification to three different classes. Our algorithm, part of what it does, it clusters. It has to separate patches into different classes, each of them sparsified by a different transform. So as it runs, it creates also a segmentation. And you see that the segmentation is quite decent. We did not impose a constraint that similar classes have to be contiguous, and yet it did a pretty nice job. So we're encouraged by it, and we think that it could be used for such computer vision applications as well. Anyway, we can use this, again, throw this into the magnetic resonance problem. So now we have, again, the MR data, but now we have multiple transforms and all that. Let's see how it works. So we applied, again, undersampling. This is the ideal object, the reference object. This is what we recover using our algorithm, quite a good recovery. This is what you would recover if you just did an inverse Fourier transform of this. So you get junk because you're missing data. So we overcome this missing data by running the algorithm. Okay, and then this shows you how the algorithm clustered the data. We allowed three different transforms. Each transform kind of adapted to a different part of the image and learned it. Okay, and then we have small errors. We do better than competing algorithms, so this was kind of a state-of-the-art algorithm. Has larger errors than what we have. We have like 3 decibels better and run faster, in fact, than that algorithm. Okay. How many transforms do you need? So we said use a bag of transforms. How many do you need to do well? Well, you think the more the better, because ideally, each patch is different. Why don't you learn a transform for each patch separately? Well, so here's what we did. We looked at the signal-to-noise ratio in recovery as you increase the number of classes, number of clusters, or the number of transforms. Things get better and better until you reach this point and suddenly you start seeing diminishing returns. So what's going on here? Why don't we keep improving as we get more and more transforms? The problem is we have less data to learn on because the same number of patches get divided between the different classes. So at some point, we have too few patches to learn reliably, and that's what happens here. So there is some optimum number of patches for which you get the best results. Okay, so this seems to work. This is great. Can you apply it in multimedia applications? Can you apply it to big data? Okay, so big data, everyone wants to do big data these days. That's where the funding goes from funding agencies and so on. So you have to do something that with a title big data in it. Can you apply it to big data? Well, we already said our scaling is better. Our transforms run faster than previous method. That's great. They can run 1,000 times faster, but that may still not be enough for real time, and it may not be good enough for streaming data. So what we want to do is this. We want to have data which comes in sequentially, for example, video frames, and you want to spit them out, maybe denoised, or maybe you want to super resolve them to get 4K resolution from HD or something like this. So we want a streaming algorithm, so you want an online transform learning. You want a method that can learn sequentially online and improve itself as the data comes in. Okay, so we derived such an algorithm that can do this, and the way to do it starts with a formulation which now has a time factor in it, and at each point we learn using the data up to that time. We can throw in something called the forgetting factor, where we forget all data. The old data becomes less relevant. We keep our focus on the present and maybe a bit into the future. So we can formulate the problem like this, and turns out that we can actually come up with an algorithm that is efficient to do this. And the reason it can be done is a kernel in our algorithm, if you remember, was the singular value decomposition, SVD. And SVD can be updated efficiently. You don't have to recompute the SVD if one column in your data changes. If you have a matrix and you change a column or you add a column, you want to update the SVD, you don't have to recompute it from scratch. You can do it in a very efficient way. So this is something people in algebra have known for many, many years. We use this trick here, plus a few other tricks, and we're able to get an algorithm that is efficient, has some optimal properties, which we can prove. And basically, this is how it goes. There is the data. We collect some data in the input buffer. We call it a mini batch. We can learn on that and spit out results. And these batches can be updated and so on. How does it work? Okay, so the natural thing to do is to apply to video. Okay, so this is a well-known test sequence. That's a noisy frame, and there are many such frames. So it's a whole video which is noise corrupted. And the goal is to denoise it, clean it up. Okay, so that'll be useful. For example, if you took a video in dark conditions, it would probably look like this. Can you get a good image? So the leader in the field until recently was an algorithm called VBM4D. And this is the error signal. So this is the recovered image minus the reference, which is a clean image. And these are errors in the result. The signal-to-noise ratio is 27 point something dB. We applied our algorithm to this. We call it viral set. So my students are very good at inventing acronyms. We learned that if you don't have an acronym, you're forgotten very quickly. People remember the acronym. They don't remember what it stands for, but neither do I at this point. But the acronym is good. So here's an acronym, somewhat suggestive of video. And we get signal-to-noise ratio almost 4 decibels better. And that's the image, and that's the residual. So much smaller residual, looks better. But you don't have to be very sharp eye to see that this actually is pretty ugly here, the hand here. And you see the error here is large. If you compare it to our competitor, the top competitor, actually they do better in this region than we do. This is actually the highly dynamic region. The guy is talking and waving his hand, and that's the more difficult part. The rest, the head, the books certainly don't move, and the head doesn't move much, so that's easier, and that's the difficult part. We don't do as well on this. We have now an updated version of the algorithm which does this well as well. Yes? Yes, it uses patches, but what kind of patches? 3-dimensional patches in space and time. So the patch is now a cube, a patch in space plus into time. So you aggregate that, so it's a 3-dimensional patch. And we learn from those patches sequentially using this online algorithm that can essentially operate in real time or close to real time. So we have kind of a newer version of this which essentially does uniformly better than this. And so we're pretty happy about it, and that seems to be a potential in working with video data or streaming data. Okay, so last topic, which I'll run through quickly. We've seen that we work on patches. 2-dimensional patches for images, 3-dimensional patches for videos, 4-dimensional patches for MR images, which are 3D in space plus time dimension if you do dynamic imaging. So you can have high-dimensional patches, but it's all patches. But a different point of view is to think about filter banks. And this is something that is familiar to people who looked at deep learning. Convolutional networks are popular. And what a convolutional network does in the first layer is actually something like this. It takes the image and filters it by a bank of filters. Each filter computes a convolution of the image with this impulse response. Now in this case, these impulse responses are the rows of the matrix W. So we can show that instead of applying W to X, W to a matrix, and X, the matrix of patches, we can take the entire image and filter it by convolution with impulse responses defined by the rows of the matrix. Okay, so this is a filter bank. It's an equivalent interpretation. And once we talk about filter banks, there is the concept of perfect reconstruction. So if you've looked at filter bank theory, what you wanted to do with a filter bank, you wanted to guarantee that after you filtered in the bank, you decomposed the data into these outputs from these channels, it was possible to recover the data back. So there is a condition. For example, if all these filters are 0, of course, not going to recover. If all these filters are the same, you'll get a blurred version of the input. You can't recover. But even though each of these outputs is a blurred version because it's convolved with this, turns out that by satisfying certain conditions, you'll be able to get a perfect recovery of the input from these guys by appropriate operation. So this is the property of perfect reconstruction. And another way to say this is this operator described by this filter is left invertible. Okay, so because I said that these filters come from the transform, the filter bank is controlled by the patch extraction here and by W. Shape of the patches gives you the shape of the filters, rows of W, the channels of the filter bank. So we have an analogy here which tells us we can do the same thing without extracting patches, but instead we can learn the transform and apply the filters to the data like this. Okay? So the point is that if W, the matrix, is invertible, in fact we had matrices which are very well conditioned, then this will be a perfect recovery filter, perfect reconstruction. Okay, so here's what we learned so far, that existing transform learning algorithms, the algorithms I described, define a perfect reconstruction filter bank. Okay, so that's just a different way to look at the same thing. But now is the new observation that requiring W to invertible is too strong. Maybe we can only require H, this filter bank, to be a perfect recovery filter bank. And now the question is, does this help? Do we benefit by relaxing the constraints? And then can we learn such a filter bank? Turns out, yes, we benefit by relaxing the constraints. Can forget about the equations. You can describe everything mathematically, but the point is we decouple now the choice of number of channels and the patch size. So we have more degrees of freedom in the design, and we can also learn. So I'll quickly show you the results, how this works. So again, we have an algorithm to learn such a filter bank. And now we're learning not a matrix, we're learning a filter bank with a constraint, the filter bank be a perfect recovery filter bank. The matrix now no longer has to have a good condition number. May not even be invertible, doesn't matter. So we apply this to magnetic resonance imaging. Again, we have an algorithm to do this, alternating between the various steps. And here's a comparison. This is our previous patch-based scheme applied starting with the various noise levels in the data. This is the result we get. And this is the filter bank formulation, and we get somewhat like half a dB or better improvement compared to the patch-based. So this new formulation, which relaxes the essentially unnecessary constraints, gives us better results. Plus, it connects this work potentially to deep learning, because in deep learning you have convolutional layers, and there's learning of those convolution filters. We have a different learning scheme, and I was just asked early on the question, can you use this for deep learning? Maybe. We haven't done that. And so that's an interesting thing to do, to study whether this is possible. I think it's a great idea. So this still remains to be seen. Okay, just as a curiosity, we said we have a filter bank. Each filter can be looked at in the spatial domain. That's the way we looked at before. But instead can be looked at in the frequency domain. How do those filters look? So these are the display of the Fourier transforms of the filters in the filter bank. And you see some interesting patterns. Some filters learn the low frequencies. Some filters learn the high frequencies. Some filters learn kind of diagonal structures. So it's kind of interesting. All of this was just learned from that brain image. And not even from the image, but from partial data, from a fraction of the data that was acquired in the MR scanner. Okay, so in conclusion, here we have a connection with filter banks. We replace the strict condition of recovering every patch by conditions of recovering the image. That gives us more degrees of freedom, can outperform the patch-based scheme. And as a summary of the whole work, we have several data-driven methods to learn transforms, different flavors, and there are more flavors which I haven't described. I think they're promising, they're highly efficient, they're scalable. We have online versions which can essentially run in real time. And so far we've studied it in denoising and compressed sensing, but there are potentially many other applications. So if you want to tinker with it, you can download papers and software, MATLAB software at this website. So I'd like to acknowledge the students. So this here says work with. Actually, it is work by. You know, the students are the ones who do the work. I get to talk about it. So these are three fantastic students. Sai graduated and is a postdoc now at Michigan. Bihan and Luke are still at my lab working, and they'll graduate at some point. So thank you.